So we stopped here. We had this plot, which is already looking kind of nice. So as a reminder, this is the time axis. Each point of time corresponds to a fit. And as I was waiting for the video to convert, I've added on each of the spectrum the error, the confidence interval. How did I do that? I had created here the vectors contain, or the matrices containing the intervals for each of the variables. So I've added them everywhere. So for example, here I plot J as a function of time and I plot the errors. And I've just added this R and double dot so that it's red and it's a dot. Just to make it a little bit nicer, I can add, for example, this. The grid always make the figures look nicer. Yeah. Now what I wanted to add on this plot, and you will see that there will be a mistake. I want to add, here is the fitted integral of the spectrum. I want to add the integral that is not fitted, but just the sum of the points. So I will go back here. Here I had defined I, but I'm normalizing it. So I'm going to remove this normalization step. I normalize directly here in the plot. So I is not normalized. So let's recall here I plot it. If I don't normalize, oh, of course I have a problem because here I asked I asked it to go from 0 to 1. So this is what I get. This is the not normalized signal integral. So let's normalize it again. Okay, so now I is the signal integral. I'm gonna add this on the plot. So I plot t from 1 to n and I from 1 to n. And let's see what we get. We see that this is now has nothing in common. This is much larger than our fit. And why don't they overlap? It's because when I did the integration, there's something I did not care about. Let's go back here. I just did the sum. Because I was normalizing, I did not care about the unit. If I want this to be a real integral, and I have to multiply it by the difference between the frequencies, meaning it's hard to explain. But this is just the sum of the y, but of the y values. But I want it to be the sum of the squares of the Riemann integral. So to do this, I'm gonna explain you in a second what it means. W is our vector containing, where is it? Here, containing the x-axis, the frequency units. So here, this is the difference between 2 points. To make it clearer, I'm going to put apps. I'll show you here what it does. So this is the value of the difference between 2 points. So now, when I plot this, oh, sorry, I have to put this. Now my sum is always the sum of a point multiplied by the difference of frequency. So I'm really summing the area as a square and no longer as just now I'm summing this rectangle here and then this rectangle, but no longer just the points. But I hope it is clear. It's really like integration. I think it will work now. So I'm going to run this code again. Oops. And now the plots. And I believe this should overlay. And it does. So now you see, we really have, in blue, it's the fit, and in orange, it's the integral, like the numerical integral, it's just the sum. You see that they overlay more or less well, but not perfectly. And what is interesting now is to repeat the Monod exponential fit, but not on the integral here, but on the fitted spectrum. So to compare, what I'm going to do, I'm going to create a new function like this. To make it easy, I'm going to start here, as I did earlier. So this will be mono exponential fits. And you do the same as I did earlier. X minus t divided by t1, t integral. And for example, here, t and I, as we did earlier. So here, the initial point is approximately 1 10 to the 9. Oh, sorry, it should be 0. 1 E9, and T1 goes from 0 to infinity, and we give it an initial value of 100. I fit it. And now I'm going to generate the code for this. I call it mono exponential fit. And I will copy it in my list of functions. I think I have to add this end, otherwise the syntax is wrong. So now I create a new section that the comparison of fits. So I'm gonna apply this one on, where is it? It's I0. So this corresponds to, this is the fit with the fitted integral, and this is the one with the non-fitted integral. I'm adding this because I doesn't have the same size. If you remember, when I define I, yeah, when I go here, I has a size of n as it was defined here, and later I've modified the length of n, which is not very intelligent way to do it, but still, now it's done. So let's run this section. I think it should work. Yeah. I have an error message. Okay, so this error, MATLAB likes to have all the input with the same, if it's base columns, it's columns, and it's rows, it's rows. So T here is a column vector, and I is a column vector, and I0 is a row vector, that's why. So if I do this, now it will be happy. Yeah. So I don't have the error message again. It's just a problem here. It doesn't start at I mean, the fit is quite poor. So let's see how we can improve the quality of the fit. Maybe I just give it a higher starting point, and maybe it will work. Yeah, now it works. So it's when you have such large values, the fit sometimes works less good. So these are our two fits, and this one is the one with the signal integral that is just the sum of the points, and this is the fitted Lorentzian. And now it's interesting to compare just gonna write. So you know, you see that this function gets two variables out. And if I don't tell MATLAB what I want to get out, it doesn't show everything here. So I have to ask it here. It's the fit results, fit res, and the GOF is this thing containing the quality of the fit. So this will be 1 and 2. Same here. Oh, I got it 2. I run it again. And now let's compare. So the quality of the fit, this is the fit for the first one. And for the second one, you see that we have slightly improved our fit. So the R square, for example, is a bit closer to 1 with our fitted Lorentzian. And the root mean square error is slightly lower. It's not incredible because the we have from the beginning we have a large, a very good signal to noise ratio, so it doesn't make a huge difference. But in some cases, doing your mono exponential fit on a fitted Lorentzian can really improve massively the quality of your fit. It just depends. Here, the quality is not too bad. Also, I have taken a simple example where it's not crucial, but this sort of deconvolution can be really interesting if you have two Lorentzian which overlay and you want to fit the T1 separately. If you just do the sum of the, if you just integrate by summing the numerical values, you cannot deconvolute them. Or you can do by exponential fit, but it is not as precise. So this Lorentzian deconvolution is really powerful. So the last thing I wanted to show you today is a two-dimensional fit. And before I do that, I would just like to be sure that you understand this syntax here when I create a function, because I think last time I haven't explained it in detail. So there are several ways you can create a function. For example, I can do this. I'm going to create a function that outputs. Oh, no, let's make it even easier. Here you can create a new function, and it gives you the syntax that you have to use from the beginning. So I'm going to call this function func1, and I'm going to make a stupid operation. So this function takes these two inputs, and what it outputs is the square of this one and this one plus 3. Why not? And when you save it, you have to save it in a folder that is active, that MATLAB that MATLAB knows where it is. So like in the MATLAB folder is obviously the easiest. And the name of the function has to be the same here and here. Otherwise, MATLAB doesn't recognize it. Now that it's done, if I type func of let's say 2 and 2, or 2 and 3, it will output the square of 2 and 3 plus 2. Oh, I did a mistake. I forgot the 1. And as you see, it only outputs one thing. It's because when you don't specify that you want all the outputs, it outputs the first one. So if I want to see both results, I have to do it like this, for example. Again. So now A takes this value and B takes this value. So this is one way to create a function, but then another way, as I said earlier, is to put it at the end of your document, and when you run your document, it recognizes it. So you don't have to create a new file. Just one comment: if you put it here, I don't think MATLAB is happy. And so now it doesn't know how to interpret this. You cannot define a function in the middle. Yeah. So it doesn't show an error message for now, but if I run the code, it will tell me that it's not happy because a function needs to be in the end of the the code. That's why I've created this section here that contains only the functions. Okay, so this is all I wanted to say about this one-dimensional fits. Now I'm gonna reuse what I've created last time, which when I created the 2D, here I created a 2D, I'll copy this. A 2D function. Just remove all these comments to make it a bit easier. Okay. So if I run this bit of code, if you remember this part of the code, this was creating a Lorentzian. This was creating a mono-exponential decay. And this was creating a 2D data that is on one axis, it's the Lorentzian, on the other one, it's the mono-exponential decay. And here I'm showing a different way to plot it. So if I run it, this was what Stuart asked us last time. This is the 2D way to represent it. This is with simulated noise and without simulated noise. And this is like in what we call in a waterfall plot. So what I want to show you is that we can do fits where we fit everything at the same time. So I cannot do that on the experimental data that I've shown you earlier, because on this data, if I show you the results again, oh, now I've overwritten some of the I have to run everything again. Okay, I'm not gonna do that. If you recall the data, they were noisy and the decoupling was moving, the central frequency was moving, so I cannot do what I'm going to do now on the simulated spectrum. This is because it was a dissolution DNP experiment, and some of the parameters are not very stable. But in a more conventional NMR experiment, you can do what I'm going to do. So I have S2D with noise, time, and frequency axis. So let's open the editor, and now I'm going to reopen. I have to give the new time axis, then W and S2D with noise. So here you see my my data as a 2D plot, and exactly as the same way as we did earlier, we can plot a multi-dimensional array, which is very convenient. So first I write the formula for Lorentzian. It's the same as earlier. Oops. Okay, so this is my Lorentzian. Here I have to write W. Maybe this is the opposites. Maybe this is time and W. I think it's like this. We'll see. And for now, it's not happy because time is not, T is not in this formula. I multiply it by this mono exponential. And you see it immediately, it obtains values that are right. Let's have a look if we compare. I had created a T1 that was 5 seconds, and it has fitted 18 seconds. I have no clue why for now, but we will have a look. The width is 10, and the central frequency is very close from 50. So you see we have obtained the actual parameters that I had entered here. I'm just surprised about this T1. Why is it so? Oh, that's the reason. Oh no, it's. I must say I am a bit confused. Oh, maybe it's simply because of this. No, this is wrong. So I must say I don't understand why it doesn't find the right T1. So let's have a look here. It goes from 0 to 50, more or less. And T goes from 0 to 55, so this is right. This is puzzling. So there must be a wrong definition somewhere. I'm not sure why, but anyway, what I wanted to show mainly is that it's easy and convenient to use this this system to plot data in 2 dimensions. So rather than plotting all the parameters one by one, what we did earlier, so we fit all the Lorentzians one by one, and then we fit this I0 as a function of time. We can just fit everything at the same time. And the great advantage is if you think about number of variables that we have here. We have 1, 2, 3, 4. If I had fitted all the spectra one by one and then fitted I0, I would have 3 parameters per spectrum. So it's a total, I have like something like 10 spectra. So it's 10 times 3, so 30 plus T1. So it would be 31 parameters, where here I have really reduced the number of parameters to the minimum, which is the 4 parameters. And finally, there are ways, so if during your experiments, W0 moves, then it's become more tricky if you want to have the same, like this is a single Lorentzian, but if you have a doublet, and the center of your doublet moves a long time, and you want to keep J constant for all the spectra, but the center, you keep it free. This is more complicated, but this is also doable. But I don't think I'm going to show that today. So this is everything I wanted to show for today. If you have some questions, I'd be happy to answer.
I have one question, but it's not directly related. I was just sort of more wondering if you knew anything about the MATLAB differential equation solver, if it was possible to have a separate, but perhaps shorter, half an hour, etc., on how to use that. But,
yes, there's
not related, so it's not an essential item.
We could do that some days. Oh, there's ODE. I thought it was the name.
I think it's OD45 series.
Oh yeah, thank you.
Quentin?
Yeah.
Where can I find this script?
The script? I'm sending it after the course. So just to finish answering Stuart, yes, there is a very simple. It's quite simple to use. So we could do a tutorial on this at some point. And Aminata, you haven't received last week the script of the previous.
I received an email. I could find the link for the YouTube video.
Okay.
But maybe I did not see those emails.
So in the video, there's a link that takes you to the script, some other scripts also, and the data that I'm using to do the fits.
Okay, thank you very much.
You're welcome. So are there some other questions about today's material?
So in the case that you want to, that you have like curves with different full width and maximum, can you do the Lorentzians for both of them and extract the width and maximum for the curve 1 and for the curve 2?
In case I have what? Sorry?
In the case that you, for example, you have like a graph with two different peaks and with different full width and maximum. Can you do the Lorentzian and obtain the full width and maximum? Okay.
I can show you an example. Just give me a second, because in fact, I have done similar things. I have a good example for that. So this is a report where I did the fits I'm showing at the moment. And so I was fitting this quadruplet, but on this experiment, I also had these two peaks together here. So let's see how I fitted them. The next experiment. So I fitted these two, I've deconvoluted these two spectra along time. And I did exactly the same thing I've shown you. So on the left, it's the results for one of the Lorentzian, and on the right is the results for the other Lorentzian. And you see that you can extract this, not the, be careful, it's not the same time axis. You can extract the T1, the width, and everything separately for both Lorentzians.